Good. So we are back with statistics. Mhm. Ooh.
I saw your email. It makes sense now.
It makes sense?
Yes.
Good.
I was very confused because we were doing the same thing.
Yeah.
And after 3 times it
Yeah.
worked. So I think it was just that it was in the range.
No. What it does, this time I cannot blame JavaScript for doing weird rounding things, because this time it's Excel that does the weird rounding.
Yeah.
And the note to myself, for these 2 questions next year, I have to set a slightly wider error range so that students don't get confused,
I was
because
really
you did everything right, but Excel gave you the wrong information.
Yeah.
Not the wrong information, but a
rounded
very
slightly.
generous information, which unfortunately. But I'm glad, because I get feedback, and that's incredibly important for me. So that
On the topic of the quizzes,
Yeah.
I was told by Dr. Curling to talk to you about any that I might have missed the deadline on over the last week. and
they're
a
all
bit.
open.
Have I not missed
No.
any deadlines?
They're all
Okay.
open.
They're all open.
I didn't do any the last week because I was in
They're
hospital.
all
They're open until the 5th of April.
everything all right?
Yeah, as fine as it is now. I'm out. I'm out and
Obviously,
about,
yeah.
sir.
Well, that
Dancing
doesn't mean
France.
anything. That doesn't mean anything, right? Because you could still
Yeah,
at
yeah.
death's
I'm just
door.
gonna
It's just
spread it
simply.
to everyone else.
Oh, I'm pleased to hear that.
So where you going?
Away from you. No, don't worry about it. All quizzes are open again, and nothing
5th
to
of
worry
April.
about.
Okay, cool.
Are they? Is there enzymes
Make
and the
headlong
skills for
starting
5th of April? Is what one?
No, one is on the 22nd, and I tell you why.
Yes.
Because this is sort of. The online quizzes are replacing the in-class test. Yeah.
Lovely.
And so there was no in-class test on Monday, obviously, but we have a 3-week turnaround for the marks. Yeah. And I said, okay, I would like to keep the online quizzes open as long as possible, but then I was told, you can't, because that replaces a test, and therefore you have to give it only 3 weeks from the ICT. FFS.
That's the one to do first.
So the enzymes
Yeah.
one
Do the enzymes by the 22nd of April.
are the by the. Thank you.
And the skills, with the skills, you should not be able to do all the skills questions of the last quiz, because we are still doing that
By
stuff.
the end of this lesson, will we be able to do it?
No,
No. Okay, we'll have to wait a bit longer.
yeah. But you've got until the 5th of April, so.
Yes.
And it's only 1 or 2 questions.
Yeah, because we could do most of the
Yeah.
chi-square.
And the enzymes, the last quiz on metabolism, you still should not be able to do it. Only by next Wednesday you can do everything.
Okay, thank very much.
Hopefully, fingers crossed. Thank you. Good afternoon. I better not pay any attention to this discussion here. Right, a most wonderful good morning, ladies and gentlemen. And the usual stuff, you know, attendance, log into Moodle, quizzes, do them. The deadline for the BI 308, I think, is the 5th of April. I wanted it actually on Star Wars Day, but they said you can't do that. May the 4th, obviously. And for the enzymes, which obviously is not this module, it has to be on the 22nd of March. So that is next Sunday, I think. Something like that. Please do them. Now, what I want to do with you today is I want to do a little bit of I've got the wrong thing here. Okay, so let's do what it says here. Let's do some genetics. Right? Let's do some genetics. Are you okay with that? Good. Dealing with proportions. Let's do some genetics. Okay, genetics. I need something that is easily testable as a sort of a phenotype. What's easily testable? What is a monohybrid and easily testable? Tongue rolling. Yeah? Can you all roll your tongue? Who can? Hands up. Roll tongue. Who can't? Oh, that's interesting. Okay, tongue rolling. Now, tongue rolling, apparently it does not have a distinct selective advantage. At least I can't see one, unless you are a very regular customer at Starbucks and you don't like the straws. So you can have your Frappuccino without a straw by just using your tongue as a straw and sucking the thing in, right? But otherwise, there is no selective pressure on tongue rolling. And it is, dominant, I think. So if you have a heterozygote, and you cross a heterozygote, only the AA lowercase is a non-roller. All the other cases can roll their tongues. I once got into a slight pickle with that because I did a talk, an admissions talk to prospective students, and we were talking a little bit about genetics, and I used this as an example. Oh, by the way, can people see it, or do you want me to enlarge the screen? Enlarge? See? Fine? Good, okay. And I got in a little bit of a problem because we were discussing that. And I said, well, if This is the constellation for rolling the tongue. And after the lecture, a student and her parents came to me. You probably can see where this is going. The parents said, we both can't roll, but the daughter can. And you think, shit. Because if the parents can't, they are homozygous for non-rolling. But the daughter can. How is that possible, they said. And I thought, what are we going to say now? Right? Ask the milkman. Now, you can't say that, obviously. So I made something up and said, oh, well, there might be another gene involved. Bollocks. There's no other gene. Actually, it's not entirely true, because about 3 months ago, I read an article where it basically questioned whether this is monogenetic. So it could be that, but why so complicated? So, be always careful with what you say in admissions talk. It can backfire. Mind you, the student attended and finished her degree with a first, so it wasn't all done. Okay, so I did the survey. Let's say, for sake's argument, we asked about 100 students here. So we have 100 students, just to make the numbers nice and clean. And I want to know, actually, by just checking how many students can roll, what is the percentage of people in the population that can roll? So here I have a sample of 100 students. That's a sample, and from this sample I want to make a conclusion about the population. Now what we have here is we are working with counts, with frequencies. I count the people who can roll, I count the people who can't roll. So these numbers that we get are typical frequencies. They are not continuous data like we've discussed the previous sessions, where we had, for example, the concentration of a metabolite or something like that. We can determine the concentration of a metabolite to the nth degree. We can say, you know, there is 23.8785936 milligram per milliliter of this compound. But in this case, we are working with discrete data. Discrete data. And we've done something like that right at the beginning of this module, when we worked with Poisson distribution, where we counted, for example, number of colonies on a plate, and then we said, okay, we can try and figure out from this sample that we have how many counts on average we would expect if we did this experiment 1,000,000 times. And we said, well, the average doesn't tell us a lot, but what we can do is we can give a sort of a confidence interval where we expect the numbers on the plate to be on average. And we did that with Poisson, and you did that in a test. So I'm not going back to that. In this case, however, we have a fixed number. So we've got 100 students that we check for that. And we would expect a certain number of students being able to roll. let's just simply forget the genetics in the first place and say, for argument's sake, what we find in our experiment is that 50 students can roll. And obviously, 50 can't. So what we have here is we have two possible outcomes. Roll, to roll, or not to roll. That's the question. Two possible outcomes, and our data are actually nominal. There is no qualification for that. It doesn't make you a better person if you are rolling or not rolling. It's just what it is. So if we've got two outcomes and we are counting discrete data, we are working with something that is called a binomial distribution. And that obviously only works for two outcomes. This could be roll or not roll, heads or tails, male, female, with some caveats, because I'm fully aware there are non-binary, and Facebook has, I think, 40 different gender assignments or something like that. So you might think that that's a little bit questionable, but in general, if you have only two outcomes, you would go for binomial. Now what we can do is, we can say, okay, from our sample, let's say we see 50 people rolling, 50 not rolling. What is the percentage in the population? And you would immediately say, well, I've got 50% that can roll, 50 over 100, that is 50% that can roll. So I would expect in the population that 50% of the population can roll from your sample. Forget the genetics in the first place. But then you think, well, it's a sample. And a sample always has an uncertainty in it. I can't be really sure that it is indeed 50% in the population. Can we actually define, again, a sort of a range in which we are pretty sure that we are right? Who can? And in fact, you can, because otherwise I wouldn't tell you that. Now, the equation for that is actually not terribly difficult, because what we can do in the first place, we can define the two outcomes. Let's say the 50 that can roll is usually abbreviated with a lowercase p. Now this is incredibly confusing. That does not mean p-value. Has nothing to do with a p-value. It's just a convention that the success, in this case rolling, gets the letter p assigned. And those who can't get the letter q assigned. And I write it like that, just to distinguish it from a 9. And we know that p plus q gives us the sample size n. So in this case, 50 and 50 gives us 100. I can also write this as p. I can write this as a proportion, as a ratio, and that is usually the more frequent definition of p. we can just simply write this as the number of success divided by the total sample. So in this case, it would be 50 over 100, and therefore that would be 50%. And we can also say that P plus Q, when we use this definition here, P plus Q always gives us 1 or 100%. So in this case, I've got 50% roll, 50% non-roll, gives us 100%. The equation to calculate the 95% confidence interval, if we have a case like that, is P plus minus 1.96. This is the magic number. We've encountered this magic number when we did the normal distribution. And in fact, it turns out that if your numbers are very large, this binomial distribution will look exactly like the normal distribution. That means 1.96 standard deviations to the left and 1.96 standard deviations to the right of your mean contains 95% of your values. So P plus minus 1.96 times the square root of P times Q divided by N, and that is the sample size. And that really has to be the sample size that we are measuring. So let's have a look at that, what we expect here. So P, we said P is 50%, or 50% equals 0.5. Okay, so what is Q? It's also 0.5 in this case. So we have 0.5 plus minus 1.96 times square root of 0.5 times 0.5 divided by 100. And if I try to do that, I get 0.5 plus minus 1.96 times 0.5 times 0.5 gives 0.25 divided by 100 gives 0.0025. Square root of that gives 0.05. Is that right? Are you impressed? Me too. So we get 0.5 plus minus, well, that would be 2 times 0.05, that gives 0.1. So we would expect the ratio of rollers in the population to be between 0.5 minus 0.1, that is 0.4, and 0.6. Or somewhere between 40% and 60%. So just by simply doing this little survey with 100 students or 100 people, find that 50 of these can roll. I can, with this fairly straightforward equation, I can make a judgment that around 40 to 60% of people can roll. That make sense? It's pretty straightforward. It's nothing terribly exciting. Right. Now, let's see what our genetics says. Genetics says these are our potential outcomes in terms of genotype, but we are only looking at the phenotype in this case. So we have 4 possible scenarios, but only one of these possible scenarios is realized as a roller. No, as a non-roller. Is this a non-roller? That's a non-roller. And 3 out of 4 would be rollers. So our proportion here would be 1/4 versus 3/4. Or here we would say 1/4, that is 25% or 0.25. And here we would have 0.75. Now we can calculate what would we actually expect if our genetics was right. We can say, well, let's the success be P again. Did I do that differently up there? Probably did. Oh, I didn't say it. Ha! P, and let this be Q. Now we can try to do the calculation again. And we can say, what do we expect if we have 75, if we have 100 people like we had before, what would be our 95% confidence interval? With the genetic data. Okay. So we would have (0.75), that's our P, plus minus square root of 0.75 times 0.25 divided by 100, and I forgot the times 1.96. Let's put it just simply there. And if you do the calculation, what you find is the confidence interval is 0.75, 0.75, yes, plus minus, and I got 0.085 if we calculate this part here. So that means our genetics actually predicts, just simply from the genetics, we predict our ratio to be between 0.665, so that's 0.75 minus 0.085, and 0.085. Sorry. And 0.835. So if we say we have 100 people, we just multiply the 100 with these numbers and we get 66.5 people. And 83.5 people. Let's say, let's do conservative rounding in this case. Conservative rounding is, we err on the side of caution. We probably say 66 and 84. And I know this is, you probably feel uncomfortable if I round the lower one down, but that is conservative because that gives us the sort of the spectrum where we say, yeah, well, we don't know exactly, is it 66 or 67? Let's go for the 66 in this case. Be on the safe side. And with the 83.5, we just can round that up. That is what I mean by conservative rounding. So the genetics tells us that we would expect between 66 and 84 people out of 100 being able to roll. But what we find is our prediction from the experiment is 40 to 60. So let's just simply draw that. So here are our confidence intervals. On the right-hand side, it's the genetics, 66 to 84. On the left-hand side is what we actually found in the experiment, 40 and 60. Now this, of course, tells us there's a mismatch. There's a very clear mismatch going on. Because from the experiment, we are 95% sure that in the population, we have between 40 and 60% rollers. The genetics tells us we should have between 66 and 84% rollers. So who is right? Well, actually, what we can say in this case is that obviously we get non-overlapping confidence intervals. That means that doesn't. but it indicates that getting this result is really unlikely. Getting the result of our experiment is not terribly likely with our genetic model. It can happen. What it basically tells us that actually, if we found, let's say, no, do it the other way around. It's a little bit like tossing a coin. And again, tossing a coin is binomial. You've got heads or tails. So if you toss a coin 10 times, how many heads do you expect? 10 times? 5, right? So would you be terribly surprised if you did this experiment and you found 5 heads? Would you be surprised? No. So what you should get? Unless you do this, like this famous scene in Friends. I don't know whether you have watched Friends or whether you are too young for that. It is heads, I win, tails, you lose. Right. It's a good thing, actually. I always win. Who is doing the washing up? It's always me. Okay, you're not surprised with 5 heads. Would you be surprised with 6 heads? You would be surprised? Would you be surprised to get 6 heads? No, not really. Could happen, 6 and 4. Would you be surprised with 7 heads? Can it happen? Can it happen, 7 heads? Yes. Mm-hmm. Actually, the answer is you shouldn't be surprised with 7 and 3. Because it's still within this 95%. Should you be surprised with 8? Yeah? You should be surprised with 8. Just about, sort of. But very, very close. It's not terribly. Should you be surprised with 9? Yes, you should. Should you be surprised with 10? Can it happen 10? Yes, it can happen, but it's not terribly likely. Yeah? Likewise, from our experiment, we say anything between 40 and 60 is not surprising. So a value of 75, for example, would we say it's not possible? No, we can't say it. It is possible that it could happen. Anything between 0 and 100 could happen. Yeah? 75 would make me feel slightly uneasy. Or the other way around, I could say the genetics says we should get something between 66 and 84. So anything outside this range here still can happen, but it's not terribly likely to get this. And if we have a mismatch like that, then we probably need to think what's going on here. Because what is going on, very clearly there's a mismatch between what the theory, what the genetics say, and what we find in the experiment. This could very well be that the genetic lies, and there might be another effect in the genetics. It could, for example, be that the rollers, for example, are less intelligent. Think about it. If rollers are less intelligent, then there would be fewer rollers at university because you have to be smart to go to university. And therefore, if you look at it, the rollers at university might be underrepresented. So we would have a bias in our sample. And that's a big, big problem when we do something like that. Now think about proportions. It always happens, proportions, when people, for example, do surveys or do polls. In America, we are going into the presidentials. And of course, the pollsters want to know who's going to be the next president. So they ask 100 people, who are you going to vote for? Are you Republican or are you Democrat? Depending on who you ask and where you ask, there might be a bias in it. Another thing is, depending on your sample size, you get a better result or not. How that? Well, look at it. We have a sample size in here. If you make the sample size bigger and bigger, let's say instead of 100, you ask 10,000, then this part gets smaller, and your confidence range also becomes smaller. So you want to ask more people, of course. You want to have a larger sample size in order to get a smaller confidence interval. Now, when can we employ this binomial distribution? We can only employ that if our sample size is smaller than 10% of the population size. So basically, if I have 100 students in the room, and I want to measure what is the ratio of rollers just in the room, not in the population, I would have to choose a sample size that is less than 10, because less than 10% of the population that I'm interested in. Also, for the binomial distribution to work properly, the sample size must be larger than 30. And by definition, this is the population, in this case, must be larger than 300, basically. Yeah, does that make sense? Now, we can also say, well, we have sort of qualitatively looked at our confidence intervals. But is there actually a way to sort of almost qualify it, quantify it? And luckily there is. Because what we can do is, because instead of just looking at what we've got here and say, oh, hey, they are not matching, we can take a slightly different approach. What we can do is, we can actually, instead of looking at these two ratios like we've done here separately, we can look at them as a difference. And what we can say is, we are not interested in the ratio of in the range of the ratios of sample 1 or sample 2 in this case, we are interested in the range of the differences. And I should say the range of the differences. In the first place, we were just interested in the range of the sample. Now we are interested in the range of the difference between the samples. How on earth are we going to calculate that? Surely this is absolutely dreadful. Actually, it's not that bad. Because all you need to do is you need to do a slight amendment. So let's say we have P1, that's our ratio for sample 1. P1 minus P2. And that, of course, is the ratio for sample 2. And we usually arrange it in such a way that it gives us a positive number, but if you really want to, we can just simply put it in absolute and just simply say we just do positives. Because life is negative enough, so let's just look on positive things. P1 minus P2 plus minus 1.96 times. What we do is, right, we are looking at a difference. So we do P1 Q1, that's for our sample 1, divided by N1. That's our sample size for the first sample. And we do that also for P2 Q2 over N2. And now you have spotted that there is a space in between sample 1 and sample 2. And your gut feeling tells you that you want to put a minus in there. Because after all, we are looking at a difference. And you should always listen to your gut feeling. Apart from this case. Because in this case, your gut feeling, unfortunately, is wrong. It's not a minus. And if you think about it, actually, it makes, to a certain degree, it makes sense. You are looking at two confidence intervals that you are basically comparing. You're looking at the differences between these confidence intervals. So the differences can be actually anything from here to here. Can you see that? It's much bigger. So in a way, what you really need to do is the sign in between here is a plus. So this here is really the equation when you deal with differences in ratios. Now P1 minus P2, we had 0.75 minus 0.5. and I've arranged it so that we get a positive number, plus minus 1.96 times square root of, and let's say we have 0.75 times 0.25 divided by 100, that was P1, plus 0.5 times 0.5, also divided by 100. That was our P2. And what we get is 0.25 plus minus I do not pretend that I can do that in my head. We get 1.96 times square root of 0.004375. Please check at home that I got that right. And we get 0.25 plus minus roughly 0.13, if we do that. But please check that I don't sell you porkies. Now, that means our confidence interval is between 0.12 and 0.38, plus minus. What does that mean? Let's remember, we are not looking at an individual proportion or ratio. We are looking at a confidence interval of the difference. And that makes all the difference. That is a confidence interval of the difference. Of the difference. And that's really important. I can't stress that enough. What does it mean? It means that we are very confident that the difference between the two samples is between 0.12 and 0.38. It means there is a difference. We are confident that there is a difference. What would be our conclusion if we had, for example, negative 3.2 and 6.3? If that was our confidence interval, we would say we are confident that the difference between the two samples is between negative 3.2 and positive 6.3. So the difference between the two samples of this confidence interval of the difference and we would say, actually, in this case, 0 is included in this interval here. It means the difference between the samples, in this case, could be 0. Or in other words, if the difference is 0, there is no difference. So if this confidence interval of the difference includes the value of 0, then it can only mean there is no difference. Between the samples. That makes sense? Now in our case, the confidence interval did not include 0. Therefore, this means it does not include 0, so there is a difference between the two samples. Are you happy with that? This is actually quite useful when you, for example, do some, let's say, ecology. You want to find out whether in a certain area, whether there is a difference between two areas. You go out and say, right, around Rutherford College, you catch some butterflies, and you look at the color of their wings, and you find it's blue wings, and you have got the red wings. And you say, okay, I have a ratio of, let's say, 20%. I count 100 butterflies, 20 of them are blue-winged at Rutherford, and 30 of them are blue-winged out of 100 near Keynes College. Is there a difference between the two locations? And the answer for that is exactly here. You just measure the two locations, the two ratios, and compare them with this equation here. And if the confidence of the difference, the confidence interval of the difference includes 0, you can say actually there is no difference between the location or otherwise. Whew. That usually it takes 2 hours for that, but I know that you are good, so I thought you can cope with that. Have a lovely weekend. Don't forget to do the quizzes.